Okay, this is lecture 6.3, volumes by slicing. So for an overview, there's 3 points. First one is area can be approximated by Riemann sums. That's something you've seen. Also, sums converge to definite integrals as the width of the boxes gets smaller. And definite integrals are evaluated using antiderivatives and the fundamental theorem of calculus. We have seen how to do this. We've seen all of these. So for a picture of this, when you have, so the area under a curve, of course, the first one can be approximated by Riemann sums. So if this is f of x, and we want to evaluate the area from A to B, we can, doesn't matter if we do lower or upper Riemann sums, either one is going to work. So the area is approximated like this. We also know how to compute the area between the curves. This is something that we are going to definitely need in this lecture. Suppose this is A and this is B. We want to compute the area between the curves. It's going to be the difference in Riemann sums. Roughly speaking, it's just a bunch of boxes. I'm not going to be so picky with how I draw them now. And again, the second point is as these boxes converge, or as the width of the boxes goes to 0, the Riemann sums converge to definite integrals, and we know how to compute these definite integrals. So those are the tools that we're going to be using in this. Okay, so the first topic is volume by slicing, and the idea is that if we have some big three-dimensional region in space, we can take a machete and just chop it into pieces, parallel slices, and just add up the volume of each of those slices. And each slice is approximately a cylinder, as we will see, whose volume is volume of the cylinder, area of the base, times the height. Okay, so let's do an example. Let me draw some figures. So let's suppose that we have some three-dimensional shape. Let's just make it like tube-ish. That'll be a little bit easier. And let's suppose it looks like this, and we want to measure the volume of this creature from between A and B. So now we're going to do something that we saw we did with the Riemann sums. We're going to break this up into smaller pieces. So let's call this interval x1. Let's call this interval x2. Let me call our starting interval x0, and let me call this end interval xn. And in the middle, let me call this one xk minus 1, and this one xk. So this is the kth interval, and then dot dot dot. So we are going to take a machete, and at each one of these breakpoints, we're going to just chop up our cylinder, and it's going to chop it up into slices. So let me draw a picture of that. So let's look at the kth piece. The kth piece, we are going to get we're going to get a cylinder. It's approximately a cylinder. In the limit, it will be a cylinder. It's slightly, not exactly a cylinder as you can see, but as the width gets smaller, it will approach that. And so here's the key point here. The volume of this cylinder is just the area of the base. I guess that is going to be, it's on the side, so this is the base, and the height is going to be this piece right here, which is delta x. So let's say that this width here is delta x. Okay, so the volume, let me use red now. So the volume Vk, I'm going to say that Vk is the volume of the kth slice. This is the area, so A, so this is the cross-sectional area at at xk times delta x. So this is the height, and so now here this is the cross sectional area at xk, and this is the height, or in this case it's the width because it's on its side. So the total volume of V is approximately equal to the sum from k equals 1 to n of the area times a or xk, or area at xk times delta x. So this is the total volume, approximately. And again, this is the reason it's not the volume is because cylinders can only be, our curve is curved and not necessarily built of cylinders. Okay, and obviously the thinner the slices, the better the approximation. So as what this means is as delta x goes to 0, we obtain, let's write this out, we obtain the exact volume via the definite interval, the definite interval. And so V is the integral. We integrate from A to B. A as so the area as a function of x times dx. Now let me box this. This is the formula. Well, you don't need to memorize this. This should just make sense. I mean, you are literally adding up the volume of each one of these cylinders from A to B. And this A of x, this is the area of the base as a depending, so this base cross-sectional area, I guess I've drawn it kind of constant here, but in general this thing could be expanded a lot. It doesn't have to be constant, it's going to be a function of x where you are down here. Let's do an example. Now, let's find the volume of the following wedge with a 3x2 base and height 1. Now I'm going to have to draw this because only way to describe what the shape actually looks like. So let's consider a wedge that is 3 by 2, and say it has height 1. So it looks something like so this is length 2, this is length 1, and let me put a back line so it's like a wedge of cheese. Now you can compute something like this using just basic high school geometry, but let's do it using calculus. Okay, so so notice that the volume is, well, let's just write down the formula that we had, and I don't think of it as a formula, I just think of it as we're going to slice it up in this direction, and we're just going to add up the volume of the slices, and each slice is going to have area A as a function of x times dx. Okay, so what's the area A of a slice? So a slice, I'm going to turn it on its side. So a slice is a triangle that has base 1 and height 2, and this is independent of x. It doesn't matter where we are if this area is constant. So A of x equals, so the area of this is 1. So this integral just becomes the integral from 0 to 3 of 1 times dx, which is x from 0 to 3, and that's equal to 3. 3 units, I'll just say 3 cubic units. Let's do a more complicated example now. Let's take this wedge of cheese, but it's the same base, but now suppose the height varies linearly from 1 to 4. So let me see if I can draw a picture of this. Okay, so as before, we have width 3, it's going to have depth 2, on both sides, that is. But now on the left side, it's going to have height 1, and on the right-hand side, it's going to have height 4. So it's going to look something like that. And let's put a 1 there. Now, let's connect that up. This will get connected down here. And in the middle, we have something that looks like that. And now okay, so this is what our slice of cheese looks like now. So as before, the volume is, well, we're integrating from 0 to 3, just the area of each slice, so a of x times dx, the infinitesimal width of each slice. So now the challenge here, the only difference is that this a of x, this area, is no longer constant. It depends on where we are down here. It's a function of x. So let's figure out what function of x it is. So I have to draw a picture. So this triangle is that triangle, and it is going to have, so one side, the height, or this side anyways, is going to be constant 2, and then the other side, this is going to be a function of x, and it's going to be this function right here. It's a function that, let me use blue, it's a function that increases linearly from 1 up to 4. So what that looks to be y equals x plus 1, right? Yeah. So down here we have x plus 1 times 2. So the area of this triangle is 1/2 base times height. That's x plus 1. So this integral becomes, so we're integrating 0 to 3 x plus 1 times dx. This is something we know how to do. So we get x squared over 2 plus x, evaluated from 0 to 3. We can ignore that 0. That's going to evaluate to be 0. So this is 9 halves plus 3. So that's, let's see, that's 9 halves plus 6 halves, which is 15 halves. And there is our answer. Okay, the next topic are solids of revolution. And we're going to start with the disk method. And here's the formula. And I don't memorize the formula. Again, if I have a picture in mind, I just know how to use it. So let me draw a picture of what this formula is saying. So let's suppose that, first of all, we have to talk about what a solid of revolution is. Let's suppose that we have a function, it looks like this, and y is a function of x. Okay, now let's revolve this function about the x-axis. So if we do that, we get, so we are revolving this about the x-axis, and so we get a function that looks, we get some solid that looks like this, and we want to find its volume. So we can do this by the slicing method, and in this case it's called the disk method. Really, they're essentially the same thing. So we want to do this between A over here and B over here. So do you see what to do? We can split up this thing into disks, into slices, and just add up those slices. And that's what this volume is going to do. So now, if we are revolving this curve about the axis, our slice are going to be little coasters, little wafers, and the volume of each slice is going to be the area of each circle times dx, and the area of the circle is pi times, so pi times the radius, so this is r. Now what is r? Suppose if this is x down here, r is just f of x, because f of x is our function. So now the area, let's write, so the area of the disk is pi r squared, which is pi times f of x quantity squared. So the volume of a slice is, let me actually draw this. So it looks like, that's a terrible drawing, but you get the point. Volume of a slice is area at x times dx. Area, we've already said, is pi times f of x quantity squared times dx. So we just have to integrate this creature from A to B. And that is, notice that is exactly where this formula comes from. Do I have that memorized? No. Just like how you don't memorize your lines in a play word for word. You just memorize them naturally, and you know what comes next just based on context. I can always derive this by just drawing the picture, drawing the slice, and knowing what the area of a cylinder is, or of a circle, and just adding that up from A to B. Okay, let's do an example. Find the volume of the solid formed by rotating the function f of x is the square root of x about the x-axis from 0 to 4. Okay, so this is exactly what we just saw how to do. So even so, I always like to draw an example. I always like to draw a picture. So this is x. This function looks like that. So this is y equals square root of x. And if I rotate it about, so this is height 2, not like that matters. This is 4. And I'm going to use red as I did before. We are adding up the volume of each of these slices. This is x. Okay. So the volume, V, is the integral from 0 to 4. I'm still going to area of x dx. I'm going to write that down because that's the slicing method. This is just a special case of it. In the case of the solid of revolution, that the area is always pi r squared. So this is pi times root x squared. That's easy to do. Dx. That simplifies as pi times x dx. So let's evaluate that. That's pi x squared over 2 from 0 to 4. And that's pi times 16 over 2. We can ignore the 0, so this is 8 pi cubic units, whatever our units may be. Okay, let's do one more example. Let's find the volume of the same little piece of that function, but now let's rotate it about the y-axis instead of the x-axis. So the first thing to do is to draw a picture, of course. So here is, give myself some room, here is that function, y equals square root of x. This is from 0 to 4. This is, of course, 2. This is the x-axis, and this is the y-axis. And if we reflect it about the y-axis, it looks something like this. Now our function is going to be, our solid of revolution is going to look like this little trumpet thing. Okay, so now notice we're revolving around the y-axis, so we want to integrate in the y direction. So our slices are going to be something like that. So let's write down our formula. The volume is the integral from 0 to 2 of the area of one of these slices. It's a function of y now, times dy. So let's figure out what this area of a slice is. Okay, so maybe I should have drawn this a little bigger, but right here, let's suppose that's y right there. Then this, I'm going to draw this disk out here. So here we are at height y. What's the radius of this disk? Let's see. So down here, if that is height y, then this has to be y squared. And that's because the y value is the square root of the x value. So this little disk here has radius y squared. And it has height y. So our volume is the integral from 0 to 2 of pi y squared quantity squared dy. And now this is something we can integrate. We're integrating 0 to 2 pi y to the 4th dy. This is pi y to the 5th over 5 from 0 to 2. Plugging in 2, we can ignore 0. We get 32 pi over 5 cubic units, and that is our final answer. Okay, we have one last method to do. It's called the washer method. So I'll give you the formula first, and then I'll show you where it comes from. So the washer method is, well, it's this formula. Let me draw a picture so you can understand its motivation. Otherwise it won't make sense at all. So let's suppose we have two functions, y equals f of x on top, and suppose we have a bottom function, something like this, y equals g of x, and we want to, between a and b, we want to take the area between these curves, so this region here, and we want to rotate this about the x-axis. X-axis is, of course, here. Now, if we do that, the cross section. So let's write this down. So let's how do I want to say this? So let's rotate about the x-axis. Now, if we do this, it's a solid of revolution. Of course, you don't need a new method to do this. I mean, if you think about it, you can convince yourself that that the cross section of this. So let me draw a picture of this. So this is going to be the cross section. It's going to be this cylinder, this annulus object. It's going to be everything that's between these two circles. Let me say that this big circle has radius big R of x, and let me say this small circle has radius little r of x. So the volume of the solid of revolution is going to be, well, the shape is going to be this washer if we rotate this region here about the x-axis. So now we don't need a new method to do this, because if you think about it, you convince yourself that all you need to do is take the volume of revolution traced out by this curve from A to B, and subtract off the volume of revolution formed by this curve, and that's what you get. So, in my opinion, honestly, it is a little bit silly to have a new method with a new name, calling them washers, but I just wanted to show you this because it's in the book, and we'll do an example problem shortly. Okay, so here, let me label this more completely. So if given this radius is big R and this is little r, notice that this top function is big R of x, and this bottom function is little r of x. And so the area of this, what I want to say, so the area of the washer is in quotes, that's this annulus area because it's in the shape of a washer, is pi times r squared of x. So this is squared. This is r of x quantity squared minus little r squared of x. Again, little r of x quantity squared. And this is pi times f squared of x minus g squared of x. So that is where this formula comes from. And again, don't memorize the formula. Draw the picture, use common sense and say, what are we doing? We're doing a solid of revolution. Each slice, so the slice at x is going to be this little piece, which when you rotate it about the x-axis is going to be this washer right here. Okay, so let's do an example. Let's find the volume generated by rotating the region enclosed by y equals x squared and y equals x about the x-axis. So first thing you should always do here is, again, draw a picture. So let's plot these things. Here's our x and our y-axis, and y equals x squared looks like this. Y equals x squared. I've exaggerated it slightly so I can draw this. Okay, so this is y equals x, and these things intersect. I could draw that like that. So these things intersect in this region right here, and this is what we want to rotate about the x-axis. I don't even know if I should try to do this. And so you can sort of see that this is going to look like that. Okay. So little r. So the upper curve here is r of x equals x squared. No, I'm sorry. The x, that's the one that's on top. The one that's on bottom is little r of x equals x squared. So the area of this washer is pi times r squared of x minus little r squared of x. So this is pi times x squared minus x to the fourth. So the volume equals the integral from 0 to 1 of pi times x squared minus x to the fourth dx. So let's do this integral because it's short. This is pi x cubed over 3 from 0 to 1 plus pi x to the fifth over 5 from 0 to 1. This is pi times 1/3 minus 1/5. This is pi times 5/15 minus 3/15, which is 2 pi over 15 cubic units. And that's our final answer.